concrete technology. And what I will try to communicate here is kind of classification of the processes we follow in this technology. I will talk a little bit about material requirements to concrete, specifically, of course, in the fresh state, and it's a very good connection to the previous presentation by Nicolas Roussel, who is also very, very active in this field of additive manufacturing. And finally, I will also present some work on reinforcement concept for concrete. You know, concrete often needs some reinforcement. Okay, let me start first with kind of a motivation. What is behind this very dynamic development in the field? So what are the driving forces? And often the people start with geometrical freedom, which is, of course, interesting for architects in the first place, but also for the users if you want to go for some kind of interesting geometrical forms. On the other hand, we, of course, can use this topological freedom for topological optimization and also introducing new functionality. So basically, we attain the same performance with less materials. And this can be interesting from point of view of the structural behavior, but also with respect to the construction physics and similar. So the next point, well, it's still about functionality and topological optimization. The next point, what I want to emphasize a little bit more is the productivity. So today we have actually a situation that productivity in construction is kind of stagnating over decades already. And from the background of the decreasing availability of the skilled labor, it's quite of a disaster. And here, introducing automation, digitalization, we can solve the problem for sure. So what you see here is also examples of some manual work. And talking about manual work, the erection of the formwork is one of the pretty laborious processes, but it's also use of material and to some extent the disposal of this formwork after the use, and this is what we can avoid if we go for the digital construction using 3D printing and similar technology. And the final point is here the cost structure. So the salaries tend to increase over the time. The price for robots is decreasing. So it seems that using robots in construction becomes more and more interesting. Finally, I want to address also the situation with the data flow. So what we have already kind of as a state of the art is a pretty wide use of digital planning tools like CAD and BIM, so that we have really a lot of data available from the planning process. And then it would be, of course, a great progress to put this data directly into the production and the fabrication of the structural members and structures. And this is what is shown here in this graph. So we want actually not kind of to stop digital process, just to planning and then print out this planning on the paper and go with this 2D plan to the construction site and then try to build something in 3D, but rather process the data further and build something according to this data. Good. Over the last couple of years, we experienced really a dramatic progress in this field. So you shouldn't try to read this slide, just kind of an overview what happens over the world. And it's a very, very kind of a fuzzy picture with quite high challenge how to navigate in this field. And this is why in Ryland we decided to go to some classification. And this classification will start first with definition of the major operations. And this can be assembly or process as such, right? And if we talk about additive manufacturing, etc., this is a process. And it's a process where we shape the structural part or non-structural part. And shaping can be done by different primary process classes. So what we are talking about with additive manufacturing, it's different from formative processes, for example, casting and a formwork, or subtractive processes where we produce some part and then we take some material away by subtraction or milling. Good. So I will concentrate on additive manufacturing only if there are also some other digital processes which would be formative or subtractive, but I'm talking only about additive manufacturing, which is also called 3D printing often enough. We have three major classes here, which are here highlighted in blue. It's particle bed binding, it's material extrusion, and it's material jetting or shotcreting. All these approaches are very good and pretty mature nowadays already. However, material extrusion seems to be pretty dominant. So most of the labs and most of also of the companies who are in this business, they follow this process. And this is why I also will concentrate today on material extrusion based approaches only. Okay, so this seems to be a repetition. Yeah, but this slide I want to show you. Going into this extrusion-based concrete 3D printing, we can have first distinction by the material deposition regimes, right? So there are two kind of cases which we can consider as a limit cases, a very stiff material. So it means going through the nozzle and placed this material doesn't flow. It just keeps the shape, the same shape as actually the opening of the nozzle. So it's on the left. And another case that material is flowable. So, well, some accelerator is added at the nozzle, and eventually it will, of course, lead to stiffening of the material. But at the moment, we consider the situation that this action is not developed yet, and so we have gravitational flow. And both these situations can be described mathematically pretty well. What we found, however, in the praxis is often this common case where we have a little bit flow, so some deformation of the filament upon deposition, but it's not very much. And this situation cannot be described by analytical formula, but rather we would go for some numerical simulation. Good. Another distinction we can make, it's by filament size. So actually, in many cases, we go rather for fine filaments to have this high resolution, to be free in shaping the material to whatever form we want. And this is what you see here on the left, where we have also resolution, which provides some voids where we maybe can use these voids for different functions, like putting the cables or whatever. Then what you see in the middle, it's a little bit coarser, printing, but often also practiced here in the practice of construction. And then on the right side, at our specific approach in Dresden, where we use coarse aggregates, very coarse filaments or thick filaments. So in this example on the right, you see filaments has a width of 150 millimeters and height of 50 millimeters. So, I mean, this distinction between fine and coarse, it's not really just formal. It implies also that we can use here very different materials. So, I mean, if we go to a very fine resolution and fine filaments, then it means we are also limited to fine sand as aggregates. So basically, we talk about here fine mortar. It still can be called concrete or fine-grained concrete if it's in structural application, so it's fine. But basically, with respect to the aggregate size, it's fine mortar. So on the other hand, of course, if you go to larger filaments, you can accommodate coarse aggregates, and then we call it real concrete kind, right? But you lose the spatial resolution, so you must kind of restrict yourself to a little bit more, let us say, regular geometries. You are not that free in this. So this is a quite important distinction. And I want to elaborate it a little bit more. I mean, going for larger filaments means also that you have quite pronounced increase in productivity, and this is what is very important in construction. I have here a little graph which shows this quite clearly, that going to larger filaments and keep at the same speed of deposition, you place actually much more material per time unit, and it's a quite important subject. And of course, this point of using horse aggregates and more or less regular concrete, it means also that you are very close to a regular construction. It means you can stick to the existing codes also in design, maybe after some little modifications. And then, of course, all these issues with shrinkage, creep, elastic models, etc. It's less a problem in comparison to fine concrete. So we had this thought a couple of years ago, and we developed a concept which we call Concrete 3D, or on-site monolithic 3D concrete printing. We got an award at Bauma. And just in a nutshell, it's about actually going for today's architectural and structural design, which means sharp corners, straight geometries, massive cross sections. So nothing really very, very fancy, but it's kind of what is needed mostly on the market. Then our concept also implies the maximum possible use of common construction machinery for on-site 3D concrete printing. And then we want to use ready-mix concrete, yeah. So not some expensive material from the back, but rather just order the material from the next ready-mix plant. And this material should be, again, in the framework of the existing codes. Then we spare a lot of trouble. So using existing standards also for the quality of the work, precision tolerances, etc. It's also part of the concept. And basically, we had a little video, which I hope will work now. Yeah, it works. Showcasing how it might be seen. We have here this mobile pump and this this mast works kind of a robotic arm here. So this was the concept. And we then started to work on implementing this concept first in the lab using gantry system to move the print head, which is pretty big in this case. And so we moved forward, and in parallel, we noticed that a company here in Germany, Putzmeister, liked the concept very much. Well, they talked already, of course, to us, and also developed, based on this concept, a real machine, which we cannot develop in this size at the university. Just too expensive. And they call this machine Carlos, and they presented this machine just last year at the Bauma, so 6 years after we got the award for this concept. And we were, of course, very, very happy that this idea came really into the practice of construction. And this person, Venkatesh Nerella, he was the first one making PhD in my group on 3D concrete printing, and yeah, logically enough, he is now with this company and pushing this technology forward. And I visited the site just a couple of days ago, and it's really very, very impressive how this machine works and has a really precise deposition of the material here. Good. So now I want to come to a little bit more detailed consideration what we all need for establishing technology like this. And I stick to this large-scale 3D printing, but what I will try to communicate now, it is also valid if you work with fine filaments to a great extent, so the difference is really minor, because it's always about the same principles and more or less the same approach. So you see here the different competencies we need in materials and machines, of course, also steering of the processes. And I will not try to cover all this. I will stay on the left side where I also have particular competence in materials. So it will be about pumpability, extrudability, buildability, and also properties of the hardened concrete. So this is what you see here. You need first to pump the material. Then you need to extrude the material. It means that material should flow out of the nozzle with a particular speed and have a particular shape after they leave in the nozzle and come in to the rest. And then you should be able to place more material on top on the deposited layer. So we call it buildability, so ability of the material to carry this additional load by the upper layers without too much deformation. And then finally, of course, we also need the properties of the hardened concrete, which we consider in the design. But basically, so this buildability and hardened concrete properties, it's kind of also the smooth transition from hardening concrete to really hardened concrete. So we have here actually more than just one stage for a structural design. We actually should also design for the buildability or for this stage of the production. Good. So let me go through these particular steps. So pumpability. Actually, we know pretty well how it works. Still, pumpability needs attention. So you should consider that it's mostly about actually the heterogeneous nature of concrete. So the concrete is heterogeneous. Nicola explained this very nicely. And in this case, moving concrete through the pipe leads to some segregation. So we have formation of lubricating layer in the vicinity of the wall. And it means also that actually this region, which is mostly sheared, also defines the movement of concrete within the pipe. So to describe actually this movement, we need to know the properties of this lubricating layer in the first place. So it's not that much about rheology of concrete as such, but rather about rheology of the lubricating layer. And we develop a technique to assess actually this situation. So it's not a usual rheometer, it's a so-called sliper, so slide and pipe rheometer, which mimic the behavior of concrete in the pipe. So basically it's a piece here of pipe which moves, and concrete actually doesn't change position in space, but it kind of also moves relative to pipe. So technically it's the pipe which moves, but for concrete it's like it moves through the pipe. So the situation is similar, and what you measure here is actually the resistance to this movement. So it's some sensor placed here at the bottom of the concrete column, and you measure the speed with which the pipe is moving, and you can change the speed by attaching more and more weights to this pipe. So basically what you get is a relationship which is similar what Nicola showed in his presentation. Just in this case, it's a pressure versus flow rate, what we want actually to get here as a possibility to predict this relationship. And you see from this equation that under consideration of the geometry of the pipe, and this is why we have here a diameter and the length, etc. But the major rheological parameters, what we use is the yield stress of the lubrication layer, and also viscosity of the lubrication layer here divided by the thickness of the lubrication layer. So to make it a little bit more simple, we convert this viscosity divided by the thickness to just parameter B, kind of viscosity parameter, and to have another normal letter, we say, okay, this yield parameter, it will be A. All right. So from Sliper, we can derive A and B, small here, like material parameters, and then put it in the equation where we use already not length of the pipe in Sliper, but a real length of the pipe and real diameter of the pipe. We get then this equation, and then we get a relationship. We can really predict the pressure depending on the flow rate in the pipe. So this is essential here for predicting actually the movement of concrete in the pipe. And of course, there are some other issues with blockages, etc., but this is I will not address today. The next point is extrusion, extrudability as a property. And since we work usually with screw extruders, I will concentrate on this. And it's really not easy to predict what happens in the extruder. We do not have analytical formula for this kind of relationship, what force is needed actually to move this complex material in the screw extruder for delivering a particular material quantity per time unit. But what we can do, can do for some numerical simulation. In this case, it's using distinct element method. And what you see here very nicely that indeed it works. So we can here process the material and deposit it. And what we can also see that we have some impression about how this tool we use in the printhead to deliver the material actually interact with the material. So this is a very good approach, very feasible approach, also to improve the designs of the printheads and also some other equipment needed for 3D printing. Well, here also a little demonstration that we also can actually simulate how well the deposition rate of the material is coupled with the movement of the print head. So on the right hand, it seems to be a good coupling, and other two examples, too fast, too slow, it doesn't bring a good result. And this is really important that you always adjust the movement of the print head, which is performed by some operating machine. It can be gantry system, it can be a robotic arm or whatever else, and actually the delivery rate of the material. Then extrudability as such. First we are interested in the quantity of the material which is delivered, and this is the best way to measure it is really just to print some material but not produce anything kind of a structure, but rather print it on the scale, and then you have the quantity of the material per time which is delivered. Of course, you can also measure geometry, and with assuming some specific weight of the material, you can come to the same result. And on the other hand, you are interested in the geometry of the filament after deposition. And basically, as long as the yield stress of the material, a dynamic yield stress in this case, after the deposition is higher than the density multiplied with the acceleration of gravity and the height of the deposited layer, then you will have no deformation, and any other cases you will have deformation of the material. And if we have deformation of the material, either it's very flowable, and again you can use analytical formula, or it's not very flowable, but also not very stiff. And then I said it should be a numerical analysis if you are interested in predicting the shape of the layer, which is interesting in many instances. Again, I will not address this. I will go to buildability. And buildability, I just repeat myself, is a capacity of the material to carry the load of the upper layers coming when we are in progress. And this is what we do in the lab. Actually, we wait till this all fails, and you see a little bit surprised expression on the face of my colleague. Well, he shouldn't be surprised because we actually printed on purpose as long until we reach this ultimate state, the failure, and then we can, from this measurement, actually test if our prediction of buildability is valid or not. So we need also this kind of experiments where we have kind of failure. So in this case, material failure, due to flow of the material, of the first one or two layers of the material. Another scenario is the loss of stability, where you have due to elastic deformation of the wall, which becomes higher and higher and higher. You have some stability issues. And I'm really talking about elasticity, even if the material is not really hardened, but it has some elastic properties and it's decisive here. And of course, it can be also a mixture of some plastic deformation plus then loss of stability in addition. So it means that here again we need to describe the material resistance. What would be also development of this resistance in time, because putting layer after layer, we also have progress in time. So it means the time runs and the material we deposited first also develops in its properties. Again, I refer here to the previous presentation by Nicolas Roussel, who described also the phenomena occurring in the material. So basically, to describe this, we use approach like described here. So it's very similar what I showed for one filament, but in this case, it's the height. It's not just height of one filament by height of the growing wall, right? And it, of course, also function of time as shown here. I hope you can see my cursor. And on the other hand, we have the initial yield stress, and then we have some development in time, which depends on the thixotropy of material. Good. We can use a formula suggested by Nicolas Roussel or by Perrault, depending on which time interval is interesting here. So at the beginning, it's pretty linear, this development in time. And to derive these properties, we need some robust approach. You can try to use rotational Riemann method, but not in the usual regime, but really start very, very slowly to capture the quasi-static properties of the material. Or you can go for this kind of penetration test or uniaxial compression test. Again, it's on fresh material, so it's a compression test, but performed on fresh material. Good. And then when you have a little bit more complex geometry than just a simple wall for which analytical formula are good enough, then again, numerical analysis is a good choice. In this case, a finite element method is quite a good choice. Good. If you ask what would be a recipe of materials we use for printing of this kind of walls for large filament printed, there are some examples. Actually, nothing fancy. We go up to 16 millimeters maximum aggregate size. So otherwise, what I want to emphasize that we need, of course, here quite a nice particle size distribution to attain also a good pack-in density, because it's a prerequisite actually for all concretes with well-controlled rheology. After producing some walls, we also, of course, want to test the properties. And here I want to emphasize that, of course, due to this layered structure, the properties will not be the same in all directions. And this is why we need also to actually take specimen in different directions, also test them in different directions. And we see here some effect of this direction. We have here so the cast specimen on the left as a reference, and you see that specifically if you test flexural strength or tension, you will see that applying the force perpendicular to the joints, will of course result in slightly or sometimes considerably low values of the strength in comparison to the direction of loading perpendicular to these layers. Okay, if I still have a couple of minutes, I would like to present a concept, or rather overview of concepts for using reinforcement. And Gonzalo, please stop me when I can reach my time limit. So I can stop anytime. Good. Reinforcement is very important. And again, we put the heads together in a realm committee on 3D printing and develop this scheme. So we recognize actually that the key criteria for kind of sorting all available and future methods in some categories is the time of the reinforcement integration. So it can be during mixing, which means that we are limited to fiber reinforcement, in this case, short fiber. So it can be during concrete shaping, which means in this case, concrete is still soft, still fresh. So, and then we have here 4 different approaches. It's entrainment, it's deposition between layers, it's a cross-layer encasement, and is cross-layer penetration. And then we have a 2-step process. So this one, it was all, or this 4, it was kind of 1-step process where the concrete is still in fresh state, and we kind of in parallel or simultaneously process the reinforcement. And if we separate production of concrete and reinforcement, then we call it a 2-step process. And then we have here 2 options. We put reinforcement prior to concrete shaping or after concrete shaping. And I will show you an example for all these approaches. And I will start with short fiber. And nowadays we have really good options to produce strain hardening materials, which means they are really good for structural design. So you need to use specific fiber to achieve that, and also matrix composition is a little bit specific. It's called SHCC. It's not a new concept as such. What is relatively new is use of these materials in 3D printing. So we started this work a couple of years ago, and the first publication was by our guest from Japan, who spent 1 year in our lab, and ourselves. And then back home, Dr. Agura, after rejoining his company, he indeed implemented this technology. And what you see here, production of integrated a formwork, right, made without any further reinforcement other than fiber, short fiber. And the benefit is you can transport this these pieces, which are pretty filigrane and have a very thin here walls. You can transport them to construction site. You can mount. There are no issues. There are no kind of danger of cracking and that they fall apart during the mounting. No problem. They also can carry quite high loads here from flowable concrete, which is filled here, so actual self-compacted concrete. And also good news, it's a really protective skin. So it's a very, very well protective material, because it's a really crack resistance. It's very tough. So, and you see, you combine here nice geometry, which is also kind of structural importance, and also very advanced technology. We use this approach also for producing some fancy shells made of this kind of panels, or rather elements which are flat. So it's all linear geometry, but putting these elements together, you can produce all kind of curvatures. And this is a multi-step process. We should first print here actually the edge, then we fill some flowable concrete, put here some reinforcement, other textile which is already kind of ready-made, or we deposit the yarns and produce textile kind of here in situ, and then some steps can be repeated till we complete the production of these elements. So we have one or two demonstrators to show already, and this is ongoing work. Some publications are submitted and you can read them soon enough. Okay, now I come to the placing reinforcement prior to concrete shaping. This would be a two-step process. And the concept we suggested for steel reinforcement is, first it's a cage of reinforcement placed here. You have then here in the middle some very thin mesh just to control the material flow. And then you just deposit layer after layer from one side and then from other side, right? And we tested this approach in the lab, so it seems to work. So it's not always great. It's specifically at the beginning of the printed process. We have some issues here in enveloping reinforcement nicely, but in general, it seems to work. So another approach is placing reinforcements prior to concrete shaping too, but in this case, it will support concrete. In the first example, it doesn't support concrete. It stands for itself and concrete stands for itself. But here we see that it's some fun example maybe here of reinforcement placed here vertically and some shaped, and we can deposit concrete on it. In this case, the shape of concrete is really defined by the shape of the reinforcement, and this is a kind of major distinction to the previous case. So another concept, also two-step process, but the first concrete, then reinforcement. And in this case, indeed, we first print here the core of concrete without any reinforcement first. But between the layers, we place this kind of pieces of metal, pieces of reinforcement. They're here crossing the filament, and they help us to accommodate this kind of meshes, which we just hang on them, right? And then it's more or less the same process what we use in repair. So when we bring some or strengthening, when we bring some additional layers of reinforcement on the existing structure. So just in this case, again, we use here the print head to deposit material layer by layer, starting at the lower, of course, position, and then coming up step by step. So this is how it looks like. Well, in this case, it's steel was made by hand, right? So, but at the moment we kind of are moving forward. So it's we have also some photographs just not looking as nice as this one. So I show you the better ones we achieve by the next occasion. And actually, it doesn't need to be steel reinforcement. We also can apply it here some textile meshes or something similar. Okay, then we come one step back and we talk about actually most interesting scenario, single step process and simultaneous here introduction or entrainment of reinforcement into concrete filaments. So we use here carbon fiber and we introduce them into the print head, and then it's kind of married with concrete and deposited together with concrete. An alternative is to deposit a reinforcement between the layers, and here you see some examples. So, well, here in one wall we actually tried kind of to deposit very different materials, which is not, of course, very practical, but it just shows the diversity we can go here for. And in this case, since it's kind of very close in time, but not simultaneous, we call it contiguous process. So this is one example. You see the fiber is deposited and covered more or less right away by the concrete layer. And again, it's a contiguous process. So during concrete shaping, And this is some further ideas what can be done. We can also interrupt the process of the concrete deposition to be able here to connect maybe a little bit better. So I don't want to go here into details. If you are interested, we published a paper a couple of years ago on this, and now we're moving forward in implementing these ideas. Here one example is shown where we implement one yarn and very thin layer of concrete going here for fine filament printing. So another possibility is to actually produce reinforcement and print concrete more or less at the same time. So, well, reinforcement comes a little bit earlier, but it follows very closely by depositing process of concrete. So it's again a contiguous project. And I don't have here more pictures on this, so maybe next time. So talking about reinforcement, you also can actually print reinforcement. It's expensive. It's also a little bit slower. But a couple of years ago, we showed that it works actually. You again need to adapt a little bit the process control. But if you careful enough, you will succeed to print vertical and otherwise shaped pieces quite nicely. So we also tested the properties of this kind of materials. And actually, it's pretty close to reinforcement we usually use in concrete construction. So it's actually even a little bit more ductile in comparison to conventional reinforcement, so yield stress a little bit lower, but basically we can work with these materials. And it's what you can build of this material. So this is actually not really for concrete construction. It's another demonstrator what you can do with this technology. It's so-called a dragon bench. So Gonzalo, if I have another 3 or 5 minutes, I would also tell a few words about implementing textile reinforcement into 3D printing.
Yeah. Go ahead. 3 minutes. Okay, good.
Oh, 3 minutes. Okay, I will be quick. So what is important when you work with fiber? It always requires some impregnation. And what we go for is impregnation not with usual polymers, what we usually have in textiles developed for construction, but it's in our case because of many actually positive features which come with this. It's about mineral impregnation. So we developed some specific techniques to impregnate the yarns with very fine suspension. You see here a mobile device we developed for that. Here you see a larger machine which actually enables us to here impregnate 10 yarns at the same time and then bound them to a bar. So we can produce this kind of one-dimensional reinforcement. We can go here for two-dimensional reinforcement. Little video here showing, and this is a mesh which looks quite similar with the metal meshes. You can go out of plane to produce a reinforcement for shell structures like this. And again, so we have here some final shape. And you can also place some concrete on it. And you can go also for three-dimensional structures. So it's still kind of dealing with reinforcement as such. It can be married afterwards with concrete. But what is more interesting than that is actually to... Okay, I think it's in interest of time. I deleted one or two slides too many from my previous presentation where I have actually the implementation of sorry. No, you notice that I'm not kind of absolutely prepared because I needed to start a little bit earlier. You remember I showed this before. I just forgot to mention that this I go just here a little bit back. I just forgot to mention that this type of integration, it was with a carbon yarn which was actually impregnated with mineral suspension, right? So it was just, I haven't forgot anything, I just forgot the sequence. Okay, excuse me for that. And this brings me to conclusion. So it's a good technology. I hope that you could get a little bit overview what's happening in the world and particularly in my group. And thank you so much for your attention, and I'm ready to answer your questions.
Well, thanks. Thank you very much, Victor. I mean, it was an impressive presentation, and we also appreciate very much that you were able to anticipate a little bit and to give the talk earlier. Actually, I was very surprised with all the things that have to do with the reinforcement, because this is the first time that I see that you are integrating reinforcement in 3D printing in such a nice way. So, are there questions in the audience?
Yes, I have one. Hello,
Sabrina,
Victor.
go ahead.
So I've been wondering, I mean, when you print the layered walls, so I assume there will be a weakness between the layers. Do you do anything special there to reinforce it, or it's enough just automatically printing layer by layer?
Yeah. Okay, it's an issue indeed. So usually we have a high porosity in this joint, indeed. We have anisotropy for sure. So we hardly can exclude it completely. We have also some increase in heterogeneity in comparison to cast concrete for sure. So the question is how much these issues are really kind of pronounced. So we have different approaches. I mean, if you deposit layer by layer with a time interval of just a couple of minutes, usually it's not an issue. Of course, it also depends on the rheological properties of concrete and also evaporation rate, etc. But if it's just small time interval, it's not an issue. But if time interval is considerable, then it would be wise to put kind of a primer on the previous layer, and so then enable really a good bond between the old layer and fresh layer. Otherwise, you will indeed have kind of a cold joint, right? So there are different scenarios how to deal with this. Basically, yeah, it's. I wouldn't say it's a point which is well answered already. So it implies that you have higher actually demand for material testing. So I mentioned this, you need to test in different directions. But it's not only about mechanical properties. So if you think about still using steel reinforcements in 3D printed elements, then it's also about durability, because this kind of weakest link, so it might be fine for with respect to strength, but it might be problematic with respect to durability due to transport of aggressive media through the joints. So it's a kind of a multi-aspect issue, and certainly not really completely solved as yet, but there are many interesting approaches how to handle this.
Okay, thank you very much. Very nice talk. I liked it very much.
Thank you.
Thank you, Rina. Any other question?
No, maybe.
Okay.
I see Pedro is raising.
Yeah, Pedro.
Pedro is raising the hand.
There's
Pedro, go ahead.
not
Pedro. Good.
Pedro, we are not hearing you.
You are still muted.
Okay.
You are still muted.
Okay, thank you. It was not allowed to speak. Okay, well, thank you. Then first, My congratulations for the big work of Victor. It's impressive how everything you do, because you are comparing, you are working in all the important issues. Then reinforcement, you talked. I was thinking in ask about the durability, but I know that this is not something new. I'm sure there are lots of aspects that you are also working. I only wanted, well, I wanted to ask too much, but I will try to reduce. One is two aspects, because you told that robotic is easy to implement, or going to low cost, the way to introducing. Then are you thinking in two ways? One is sprayed concrete, and the other thing is using also by robotics a temporal framework, because you can working with a sprayed against a framework that can move, like a sliding framework or something like this that can works. Maybe also thinking in rheology, that is the topic, using also sitting time control. I don't know if you are working also in those points.
Well, we in my group do not work with kind of move-in formwork, but it's a very interesting concept. So maybe it's kind of what you refer to is concept like it's developed in Zurich, Smart Dynamic Casting, which is kind of a move-in formwork, which is very short one, and also kind of a formwork which can change its shape so that you can have at the end of the day different cross sections over the height. So it's very interesting. It's very interesting. It's not easy to handle. So I'm familiar pretty well with the work running in Zurich, and I admire this work. But I also understand that there are many issues which can be solved in the lab very elegantly, but which is kind of a challenge for from the practical perspective, where we have much higher, of course, scatter in the properties, and then you notice, of course, this in the quality of the fabricated part. I'm not sure if it meets the core of your question, but this is what I understood. What
No, maybe the question is to start a new presentation. I know that this is difficult. There are too much aspects that can be incorporated also, no? Because you are moving also with the type of rheology you need for the concrete. Is not the only pouring the layer by layer, but the options of sprayed concrete can guarantee more the connection between layers.
Yeah. You mean combining layer by layer deposition with some support by formwork? Is it what you mean?
Yeah. Yes.
Yeah. I understand. Well, it's the question how to do it. I mean, as a concept, it sounds good to me, but I'm not sure that it's kind of very practical. What we have is some temporal supports, not by robots, but rather by material we then actually get rid of. So kind of a light material which is recyclable, etc. So we print it as a support, for example, for some horizontal elements. Right, and then because we cannot print just over the air, right? So we need some support. So we have some work on this. So printing this support from some disposable material, then get rid of it. But it's a little bit different what you suggest, using some robotic arms for this kind of support. Okay, but I understand that time is running, and probably it's good time for me to say goodbye?
No. This is. I am thinking only in the future, because this is a work for the future. This is difficult to apply. It's beautiful to apply for a aesthetical or more. But I think we have to think in an industrial production, in something that can be applied for normal constructions, not only for the more beautiful or more difficult cases.
Yeah. For this, our concept Concrete 3D, and what puts my cement of it is Carlos' machine. I think it's a good example.
Okay, thank you very much,
you.
Pedro. Thank you very much, Victor, for your very nice presentation. I hope that we can meet in person next year in Dresden again in this